2, 3, 4, 5, 6. All right, here we go. Oh, yeah, thing's buzzing. All right. Hey everybody, let's start the thing. So here's what we're gonna try to do today. 7.3, 7.11, 7.75, 7.33, 7.35, 7.44, 7.57, 7.68. All right, so take out your books, take a look at these questions, and we're gonna try them. And we're just gonna go as fast as we can because I don't want to be here too long. Long ass questions. All right, first question. Sketch curves. Is this really what I chose? Gross. All right. 7.03. This one stinks. I don't want to do it. Yeah, no, I don't have enough mental energy for doing a weird graph question tonight. Let's do 7.11. Oh yeah, 2 people showed up, and they can watch me decide not to do questions on the fly. Wait, no, right. Oh, you're right. I gotta change the thing for this. All right, hold on. Wednesday, November 2nd. And I gotta delete the Mazur part. All right, good. Yeah, I know, Joseph Lee. So Joseph Lee's scolding me about the date on the video, but I fixed it. I think. I don't know. Technology, you know? All right, so let's make sure we're all cool. Yes, we're all cool. You can see me wiggle the pad. Good. All right, let's start trucking. 7.11. 2 blocks are held together with a compressed spring on a slippery table. 2 blocks. Compressed spring. Yes. Okay. One block has 3 times the inertia of the other one. So this has M. This is 3M. When the blocks are released, the spring pushes them away from each other. Goes that way. Yeah, let's stick the spring to this guy. Goes that way. All right. So, what is the ratio of their kinetic energies after release? Oh, this is fun. All right, so check it out. I want the relations of their kinetic energy. I'll call this block A and block B. Yeah, sure. A, B, V, A, B, B. Here's the thing. Total momentum is conserved. Total momentum is initially 0. So afterwards, 0 is equal to 3mva plus minus mvb. Here, you know what? I'll just put vector signs on them. Minus. All right. So the moral of the story is, because of conservation of momentum, their speeds can't be arbitrary. They will have to move with this relationship where the heavy object moves less fast than the light object. All right. So, oh, this is neat. So this is 3VA is equal to VB because the M's cancel out. And I want the ratio of their kinetic energies. So this is 1/2 mv squared. This is 1/2 mab squared. So this is 1/2 3mv squared. A, B, This is 1/2 mvb squared. Cancel, 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 cancel. 3 va squared over vb squared. And this is 3 va squared over, right? Can you see that? Yep. All right, so the deal is that stuff happens in common. 9 va squared vb squared and 1 over 3. That's the ratio of their velocities. That should say A. All right, done. Conservation of energy, conservation of momentum. Well, I guess conservation of energy didn't really show up too much. Yeah. I'm surprised they didn't ask about potential energy, given that that was in the potential energy section, but what are you going to do? Next question. Let's see if I can zoom out just a little bit. All right. Is that... Hopefully that might be a little bit better for you to see. All right, what's the next question? 7.75. Dig it. 1, 2. 7.75 goes like this. The observation deck of the Washington Monument is 152 meters above the ground. How many king-size candy bars, each supplying 1.3 megajoules of energy, must an 80-kilogram man consume to replenish the energy he expends climbing the 825 stairs to the observation deck? Here's the Washington Monument. It's very tall. Here's your dude. He's happy because he gets to eat chocolate bars. Alright, so here's the story. He's going to go up inside and end up at the top floor where, I don't know, there's an observation deck. Who knows? I don't know. Now here's the deal. This is a story about energy. Whether you want to know it or not, this is a story about the different types of energy. KE, potential energy, source energy. Okay, so initially he has source energy. KE is 0 because he's at rest, and potential energy is 0 because he's at rest. And then he climbs the tower. Source energy goes to 0. Kinetic energy, also 0. Potential energy at maximum. So all the source energy turns into kinetic energy, turns into potential energy. U. So the question is, how much source energy does he have? And the answer is, it's the amount of potential energy that he needs it. And how do you figure out the potential energy? GMH. Change in height times... Oh, geez, I stepped on the thing. Gravity. Oh, man. You know, during the exam, during the last midterm, I lent 9.81 times... let's see, how was this guy? 80 kilograms times 152. You know what? I bet I could find my nice calculator. Anyway, yeah, so I lent out the good calculator. See, this is one of the forbidden calculators. This one. I don't know if this is actually one of the forbidden calculators, but it's a forbidden calculator. And so I confiscated the forbidden calculator and traded one of my nice stupid calculators, and now I don't have any calculators. Well, I've got one. I don't know where it is. Hold on. Oh, jeez, I'm tired. All right. Yeah, see? Screw you, crummy calculator. I've got this one. It also has an advanced Dell system. What's the difference between these? This one's the 520X and this is the 510RN. This one's a registered nurse. Alright, so let's get this back on the go. Let me see. Alright, so 9.81 times AT times 152. Oh, jeepers, look at that. 19289 joules. That's a lot of joules. There's a lot of joules in the Washington Monument. Alright, so one candy bar, 1.3 megajoules. So this is 1.3 E6 joules per candy bar. So how many did we use? We 119289 divided by 1.3 E6. 0.3 E6. Oh, he didn't even use 10% of a candy bar. Less than 10% of a candy bar. Okay, which is just to say that if he goes up and down 10 times, he can eat a candy bar and it's fine. So, hello. Next question. Next question is 7.33. How do we do that? 7.33, I don't know what these questions look like. FYI, here's what I do when I choose the questions. I open the book and I find the questions on your assignment and then I look at the questions near them. And if I go, yeah, that one has numbers, I'll add it to the list. Okay, so this one goes this. A 0.01 kilogram bullet is fired from a 5 kilogram gun with a muzzle velocity of 250 meters. Meters per second. While the bullet is traveling in the barrel, what is the ratio of the acceleration of the gun to the acceleration of the bullet as a function of time? Actually, that question's pretty easy. Where does it come from? It comes from the conservation of momentum. What do I mean conservation of momentum? It's because, if P total is equal to P1 plus P2, then the derivative of P total is 0, which means the derivative of P1 is equal to the minus the derivative of P2, and these translate to accelerations. A2, and so A1 over A2 is equal to minus M2 over M1, which is not surprising. We knew that. Oh, there's a potential energy question. All right, come on, keep on it. 3-3, where are we? So this is ratio of the acceleration of the gun. So so this is the mass of the bullet divided by the mass of the gun. So that's 0.01 divided by 5. So that's 0.002. That's the ratio. What is the speed of the bullet relative to the ground at the instant? Oh, you know what? This is really neat. I never understood the phrase muzzle velocity, but now it kind of makes sense. Here's the idea. It's got to be the relative acceleration, or sorry, the relative velocity of the bullet to the gun, right? So here has the bullet, here has the gun's velocity, and the muzzle velocity is V bullet foot gun. And that is, in this case, 250 meters per second, which is V gun, V bullet minus V gun. Okay, now, here's the thing. We want the bullet's velocity relative to the ground. How do we figure that? I know. How about conservation of momentum? It's because P of the gun has to equal minus P of the bullet. So V gun is equal to minus V bullet, mass bullet, over mass gun. All right, I just wrote gun here and flipped over there. So you can substitute this up in here. 250 is equal to VB plus and then you solve it. $250 divided by 1.002. So this is 249.5 meters per second, and then VA is going to be minus 0.499 meters per second. All right, let's see. We got the questions at the back of the book. Let's see what I got. So it's the same answers, odd number questions. Here we go. Oh, I'm hungry. Oh. Okay, yeah, these are right. These are the same answers that the book gives. So, I'm right. Way to go, me. Alright, next question. Do you ever get really, when your eyes start to get all sleepy? Because you're tired? What happens to me sometimes? I die in here. Alright, back to it. 7.35. Let's do it. A glob of putty is thrown to the right, bounces off a cart, initially at rest on low friction tracks. The collision takes some time. It's a coefficient of restitution question. I don't want to do this question. I'm not going to ask you guys coefficient of restitution questions on the midterm, because those are terrible. All right. Oh, here, hold on. Someone at the door. Hey, what's up?
Going really well.
Okay, good.
People did amazing. Like there's like really really high grades for it.
Oh.
They seem to get it. And the people that usually don't do great told me that the example was really useful.
Okay, good.
The other people that just normally do pretty well, I mean, obviously they didn't really care, but about the example. But the people that needed it worked. And I think this one was just really well timed. Like the amount of time that they had. I only had one group that was like sitting around a little bit. They were only they were only sitting around for like 5 or 10 minutes. But everybody else like just kind of finished up in time.
Okay.
And they got it the whole way.
All right, groovy.
Good.
Thanks.
Cool.
All right, I don't want to do this question. No more question. Okay, why don't I do question 7.42? That's not on the list, right? Yeah, alright. Guess I better go change this in the thingy. So read 7.42 and then I'll do it. Okay, so it says the potential energy of an interaction is given by a blah x squared. If the initial speed of a blah object in the system is blah, how far does it travel before it reaches that speed? Does your answer depend on whether an object is traveling in the positive or negative x direction? Hey, that's a pretty fun question. I'm glad I chose it. Thanks, Ants. Alright, so let's draw this. The potential depends on position. And this isn't rare. We ended up with kind of an equation like this in gravitational potential energy. And it's something I tried to emphasize in the lecture, which is that if your object has a potential energy, it means that it's storing energy in some kind of coherent deformation. And if that's the case, it means that there's a relationship between the geometry of the object and how much energy it stores. And so the result is that you can relate how much energy it has to its position. Position is a geometric quantity. So here's what we do. Imagine you have, I don't know, some kind of spring. In a spring. Okay. When the end of the spring is at x is equal to 0. Alright, well, whatever. When this end of the spring is at x is equal to 0, it will have this much potential energy. Is that right? Okay, well, whatever. You know, often often this drawing isn't the best when it comes to springs. Often what you'll do is you'll say, here's the wall, and then there's a spring attached to it, and then the end of the spring is at x is equal to 0, and then if I bring the end of the spring over here, it means that I will have deformed the spring. Yeah, that's probably what this corresponds to. Okay, so if it goes out, it's stretched, and if it goes in, it's squished. If the initial speed of a 0.82 kilogram object is 2.23 meters per second, when x is equal to 0, so here's our object. I don't know, it's being pushed or something. This is 0.82 kilograms. And it's traveling with speed 2.23 meters per second. How far does it travel before it reaches speed 0? Okay. And here's the idea. The overall idea is that we're dealing with kinetic energy. Total kinetic energy. We're dealing with potential energy. Okay? So initially, the potential energy is 0. And the kinetic energy is 1/2, 0.82. Oh, you know what I could go for right now? Some Chinese food. Maybe I'll phone my wife and ask her if we can get Chinese food tonight. Wouldn't that be great? 2.04 joules. Okay? So the total energy in the system is that much. Afterwards, at this point in the game, there is 0 kinetic energy, so there must be that much potential energy. And the idea here is that there's a relationship between, like I said, the geometry, the position, and how much potential energy is stored in it. So U is equal to 6.4. Yeah, man, some Chinese food would be real good. So that's X is equal to 6.4. No, 2.04 divided by 6.4. Square root answer. Okay. So, that's the answer. That's how far it has traveled. And now, the question is, where's the question? This is 4-2. Does the answer in part A depend on whether I was going this way or this way? If I'd been going this way, would the answer be any different? Well, if I was going this way, there would be also a point where it had compressed a lot. And at this point in the game, kinetic energy would still be 0. Potential energy would still be this one. And so the deal is, nothing about this equation would change except that this would be a minus. It would have gone to the left. Same amount of energy. How do we answer this specific question? Does my answer in part A depend on whether the object is traveling in the positive or negative x directions? Does the answer in part A depend on initial directions? Well, okay. So when we answered the first one, we said the final position was 0.565 meters. When we answered it the second time, the answer was 565 meters. The original question is, and I quote, how far does the object travel before it reaches a speed of blah? And you note that both of these are the same distance from x is equal to 0. So dig it. The answer to this question, does the answer depend, is no. Happy? Well, clap your hands. Time to do another question. 4.44. Oh, this one's done. 4. A block heart and a block heart are held together with a compressed spring between them. Okay. When they're released, this cart, boop, boop, boop. Oh, you know what? This question, all right, to do this question, I messed up the order. It's not too bad a question, and I could do it without it, but let's just keep everything straight. The question, as it's stated, says this one's on the right and this one's on the left. Okay. So it says, when they're released, this one moves at 1.1 meters per second. And it wants to know how much elastic potential energy was stored in the spring before the release. Alright, well, kinetic energy initial is going to be 0. Kinetic energy final is 1/2, 0.12. I guess I better find this one. VA squared plus 1/2, 0.36, 1.1 all squared. Right? This thing needs to be focused. Focus. Oh yeah, dude. Every time I do this, I forget to focus. It's been legible, I think. Alright, so here's the deal. At this point in the game, all the potential energy has been released. So once I calculate the total kinetic energy here, U is equal to 0, I can figure out how much potential energy there was at the start. So how do I do that? I need to figure out what my speed is here first. How am I going to do that? Well, I don't know. How about the conservation of momentum? So, the initial momentum is L Zilcho. Why? It's not moving. So the final momentum is going to be 0, which is, how about if I go 0.12 VA, I'll leave this as a vector, plus 0.36 times 1.1. A velocity is going to be 1.1 times 0.36. Nope, 1.1 times 0.36 divided by 0.12. So the final kinetic energy is going to be 0.5 times 0.112 times 3.3 times 3.3, boop, plus 0.5 times 0.36 times 1.1 times 1.1, boop, 0. Really? 871 joules? That seems awfully low. I'm going to do this question again. 0.5 times 0.12 times 3.3 times 3.3 equals plus 0.5 times 0.36 times 1.1 equals. Alright, I guess it's right. So U initial is equal to 0.871 joules. It's a lot of joules. You know who likes joules? Pirates. 7.57. There's not many. Oh, did we already do? Yeah, so last week it was the relativity problems, right? We did a whole bunch of relativity problems. Sorry, I was just like, why haven't we done any relativity problems? It's foolish. Alright, 5.57. You lean out your dorm window, which is 12 meters above the ground. And you toss a 0.12 kilogram ball up to a friend at the window 11 meters above you. What's the slowest initial speed at which you can throw the ball so he catches it? If you throw out the ball at this speed and your friend misses it, what is its kinetic energy the instant before it hits the ground? How tall am I? Oh, okay. So you're starting 12 meters above you. Jeez. So here's your here's your friend's window, and here's your window, and here's the ground. Hey, look, everybody, there's a French bulldog outside. We can't look. We're too busy gallivanting around, throwing snowballs at each other. Okay. So, right, you need to say that this distance here is 12 meters, and that this distance here is 11 meters. Okay. So, this question's fun, except that, so during the midterm, say, we did questions that were kind of like this, and you had to do them using essentially the constant acceleration equations, and that made them horrible. But the nice thing is we figured out how to use potential energy, and that means that instead of keeping track of where the objects are at what time, all we need to do is keep track of how much energy they have at different times. So there's a variety of different ways of doing this, to tell you the truth. I can do it two ways, and maybe I'll do them to illustrate them. There's the total energy method, and then there's the change in energy method. So the total energy method is to say that there's some total energy, and it's made up of potential energy and kinetic energy. And the change in energy method is to say that the change in potential energy is equal to minus the change in kinetic energy. They both give me the same value because it makes sense. This one comes from this one, and this one comes from that one. It's fine. It's the same. It's the same mathematics. So more interesting, the change in the potential is equal to the mg times x final minus x initial. Okay. So for the total energy, you need an equation describing how much total energy there is. Okay. So to do that, we need to set where the energy is zero. So let's set the potential energy to be zero down at the ground. Okay. And that means that at this moment here, when the ball is here, it has potential energy, mass times gravity times 12. That's the U. And it has kinetic energy, I don't know, KE. But more importantly, when it's at the top of its arc, it has gravitational potential energy m times g times 23, because it's 23 meters in the air, plus KE is equal to 0, because it stopped. That height, it's got no kinetic energy. Okay? And what this does is it lets us calculate the total kinetic energy here. Real lickety-split. The mass is 0.12 kilograms. Gravity 9.81 times 23. So there's 27.1 joules of energy here. And when it's at the start, we want to know how its initial speed is, right? So at the start, it must have 27.1 joules. This potential energy is mass is 0.12 times 9.81 times 12. Nope, 12. 14.12 joules. Kinetic energy here is 27.1 minus 14.1. 13 joules, which is 1/2 mv squared. So V is 14.7 meters per second. Like I said, we can use the change in potential energy just as well. So the idea being that as the ball goes up 11 meters, its change in potential energy is going to increase by mg times 11. Whoa, what the donkey punch? You didn't hear me say that. Sorry, the computer just flipped out. Sorry. 9.81 times 0.12 times 11. So we know the potential energy has gone up by 12.9 joules. And so the kinetic energy has decreased by 12.9 joules. The kinetic energy at the top is 0. So the kinetic energy at the throne is going to be 12.9 joules. And you can calculate how much speed that is. So that's equal to 1/2 mv squared. .7 meters per second. I'm sorry for saying donkey punch just there. I've been trying not to curse, and so my brain just fills in whatever stupid sounding thing it can. Oh, I'm embarrassed. I'm the worst person. Well, sorry. Alright, if you throw your ball and you hit the... Okay, so next question. If you throw the ball at this speed and your friend misses it, what's its kinetic energy before it hits the ground? So at the bottom here, U is going to be 0. So the kinetic energy is going to be 27.1 joules. So you can use that to figure out how fast it's going. Nope, not that question. Which word? 57. Suppose you throw the ball directly downwards at speed calculated at part A. What's the kinetic energy before it hits the ground? Oh, okay. So the question says, hey, instead of throwing it up, what if you threw it down at the same speed? If you threw it down at the same speed, the kinetic energy would be the same, potential energy would be the same. So the kinetic energy when it hit the ground would be the same. So, what now? Jeez. 7.68. Oh, this is fun. A 0.7 kilogram basketball dropped on a hardwood floor rises back up to 65% of its original height. If the basketball is dropped from a height of 1.5, how much energy is dissipated in the first bounce? Cool. Okay, so what's up with this? This is a conservation of energy question. So it has some initial height. So it has some initial potential energy. And then when it's down on the ground, it has some kinetic energy. And the idea here is that at this moment, the kinetic energy is equal to the initial potential energy. And then it loses some energy. But it has some initial kinetic energy, and then it goes back up to some maximum height, U final. Okay? So, KE at this moment is going to be equal to the final kinetic energy, potential energy. Why is this useful? It's useful because what we've been given is the ratio between this height and this height. So if it's 7 kilogram gas, right, so if this is 1.5 meters, 65% of its original height is 0.975 meters. Okay. So the deal is that there's a relationship between how much potential energy and the height. Okay. So so if U is equal to mgh. So if, what was the answer? It's 68, sorry. So if 65% of the initial height, the initial energy, ends up as the final energy, the thermal energy created is going to be 35% of total energy. So in other words, each time it bounces, the ball loses, the system loses 35% of its total energy. Okay? And it's important for you to see how I'm applying the concepts we've been talking about in the lecture to figure this out. The idea here is that there's a relationship between the total amount of energy a system has and its maximum height. Right? So when it's at its maximum height, all of the system's energy is in potential energy. So we can calculate that. And reliably, if the final height, the maximum height, goes down by a certain percentage, it means that a certain percentage of the total energy remains after the collision. Alternatively put, a certain percentage of the energy gets lost to thermal energy. All right? So, we can use this to answer this question. Every time I look away from the textbook, I lose the question. If the ball is dropped from a height, how much energy is dissipated on the first bounce? So, the initial energy is 0.7 times 9.81. This is mass, g, height, 1.5. I like that one. It's hard font. Okay. So 35% of this gets lost in the first collision, which is total energy times 0.35. So that's 3.6 joules of energy gets lost in the first collision. How much energy is dissipated in the fourth bounce? Okay. I'm sure there's a really easy way to do it, but I don't. Alright, so on the 0th bounce, on the first bounce, on the second bounce, on the third bounce, on the fourth bounce. After the first bounce, after the second bounce, after the third bounce, after the fourth. In the first bounce, there's 10.3 joules. It retains, 65% of its energy. So this is 6.695. Second bounce, it retains 0.65 of its energy. That's 4.35 joules. Third bounce, 0.65. Oh, you can't see it. It's not shining in the light in it. I'm sorry. 2.828 times 0.65, 1.838. So the change between these two is it loses 0.989 joules. So it loses about a joule. And to which type of incoherent energy is the dissipated energy converted? It's turned into sound, heat. You dribble a basketball enough, it gets hot. But mostly it's sound. I think it's pretty loud. Well, I don't know how much a joule of sound is. Anyway, yeah, it's pretty loud. Dribbling a basketball is really loud. So my guess is it's mostly sound, but there's some heat there too. Okay, next question. Oh, that was the last question. Any other good questions in this book? There's fundamental interaction questions. Question 2.28. Explain why friction is not considered a fundamental interaction. Can you imagine that on a midterm? Ugh, it'd be like marking mud. Why isn't friction a fundamental interaction? Friction is essentially an interaction that turns coherent kinetic energy into incoherent kinetic energy. But the energy, the interactions themselves, so the degree to which it happens depends on the surfaces and what they look like on the microscopic level. But in the end, it's still just the Coulomb force that they're interacting with. I don't know. All right. Well, what other questions are there here? Interaction range. Source energy. That was fun. Interactions and accelerations. And we did those. Non-dissipative interactions. Yeah, potential energies. We did those. Energy dissipation. We did some of that. Potential energy near Earth's surface. We did that too. Dissipative interactions. Yeah. Well, okay. I guess that's it for today. Well, we've been here for an hour, more or less. So yeah. The moral of the story is you shouldn't curse kids. It's bad. Yeah. I guess I'm done. So I'll see you later. I think what's going to happen with the practice midterm is I'm going to make a practice midterm. I'll try to upload it shortly, but I will. I'll give it to the TAs for the tutorial for the SL session, tutoring session thing. And maybe you can bring it to there, and they'll tell you what the answers are. Yeah. So, until then, have a nice day.